Right, we will actually see polyfold regularization completely rigorously stated and a little bit in action. So, and again, I'm going to shamelessly copy the theorems in our version from this first and second look. Hopefully not terribly skewed. And I'm going to retreat to the Gromov-Witten type case because I want to not confuse you with boundary at this point. So we're now thinking about a moduli space that really we don't expect to have boundary. Unlike this Morse space from last time, that where the broken ones should be the boundary. So we're looking at our favorite Gromov compactified space of pseudoholomorphic spheres in a fixed homology class. And in order to get myself into the M world, I'm going to assume that all the stabilizer subgroup are just the identity, which gets me into the M-polyfold world, where I don't have to think about categories. So no morphism spaces today. Right? And our favorite statement, again, is that this compact moduli space ought to be the zero set of a section. And so we spent a considerable amount of time on trying to understand what the base space looks, from which this thing gets cut out. Right? So it then actually is a subset of some big space. And, roughly speaking, again, this should be, maybe maps of a certain regularity, moderate parametrization, and then bubble trees of also not necessarily holomorphic maps. So here there's, splitting of the homology class. There's some fiber product going on. This is the first term, similar to the once broken Morse trajectories that we had last time, and then in general you can have more complicated bubble trees, so this gets worse. So, and then get ourselves grounded again. Roughly speaking, our bundle over this should be exactly what the d-bar operator takes values in. So whatever the base point is here, let me write this as equivalence class of some tuple of maps. So for every point in here, I need to say what the fiber is, and that should be some 0, 1 forms also of a certain regularity of, well, all the pullback bundles over all the components. So that needs to get some kind of smooth structure. And then we would like our section to take all these components. Right? So really there will be some kind of tree, and for each vertex there will be a map. And we'd like to make sure that all those maps are holomorphic, so apply the d-bar operator in every component. So that's, roughly speaking, as a point set, a map from this set to that set. And it's a section because there's a projection down so that the composition is the identity on X. Presumably it's even continuous because that's what the Gromov topology does for us. Right? But now we'd like some kind of smooth structure so we can actually talk about Fredholmness. And that starts with a smooth structure on the base. So somehow including the pre-gluing, so a neighborhood of these once broken or maps with one node together with some smooth maps. We convinced ourselves that you could model that in some kind of weird subset of a scale Banach space. Right? So the weird subset was this splicing Coro image of a retraction. And the nice space now is, unlike the Morse trajectories, we need to now take maybe H3, so we'll show that we're in C1. And then we have maps from, well, the sphere. I'm trying to write down a unique a Hilbert space here that doesn't so much depend on where I trivialize. So, I can trivialize all symplectic bundles over a sphere to just a CN, trivial CN bundle. Right, so H3 on the sphere of values in CN, then will need to be some kind of fiber products, and, well, I should also take the hypersurfaces that satisfy some slicing conditions to fix the automorphism action. I could encode that actually in the splicing core. Right, a hypersurface is the image of a very simple projection. So, so this is, right, and then, right, so these are the nearby nodal ones, and then there should be a gluing parameter. And the nice thing is that now the gluing parameter is really just an open set in C, so no boundary in the picture. So that's very roughly what I lost all my other prep here. That is sad. All right. So similarly, right, I would like Y to now be modeled very similarly. Well, Y is the total space, so I certainly need the base, all of this. And then I need the fibers. And the fibers will be something, well, it's a d-bar operator, so I'm just going to be in H2. Need to put some scale structure on this. And hopefully I can also trivialize my bundles here again, so you should see this. No more fiber product going on here. Because at the node you really have, the d-bar operator on one side of the node and on the other side of the node, they don't agree. So this is what we would like to just, well, so what, this is the big ambient spaces, so this is now, this is the scale Hilbert space in which my fibers will lie, right? At gluing parameter 0, this should be the fiber, and at gluing parameter positive, somehow I'm going to have to put my fiber into this space with this anti-pre-gluing. So that's where the all of the splicing cores of these retractions somehow come from, well, having a useful idea of what's going to be onto as a chart. Right? That's always going to be the plus gluing, and then there's going to be an extra minus gluing that keeps track of what you've lost. So, right, so the plus gluing here. Now, honestly, in nonlinear cases, gets from the pullback tangent bundles over the nodal curve to the pullback tangent bundle over the pre-glued curve. And this is then something that you can really nicely use as a chart map for the nearby points in your polyfold. What you've lost there, right, is at a point, what you're losing is somehow a little neighborhood. So, and you're losing all the information here. And you can think of this as information that is parameterized by a cylinder. This sort of two half cylinders here. But it all happens in a neighborhood of the node, so I can pull all of this information back just to the tangent space at the value at the node, these two right? So U0 minus and U0 plus are these, well, bigger spheres. So really I have pullback, I have sections in the pullback tangent bundle here, but near the nodes they really sit over, well, you know, a point very close to the node, so I trivialize my bundle there. Just think of this as a map from the cylinder to the tangent space at the node. That's this space here. That is actually going to be important on some level. So, and you know, on the fiber, I can do pretty much exactly the same. Well, I'm lying a little bit, right? So here there needs to be slicing conditions and a fiber product for the node, and here there isn't. So it's a slight, tiny, up to finite dimensions, it's the same kind of pre-gluing and anti-pre-gluing. But again, and also I'm now not in the pullback tangent bundle, I'm in the 0-1 forms on the pullback tangent bundle. And so, but yeah, I can do the same kind of interpolation and shifting procedure. And so the fibers ought to be 0-1 forms near the, or over the pre-glued curve. Because that's where my D-bar operator lands. And then, well, I could also take 0-1 forms over the cylinder, but the cylinder has nice S and T coordinates, so I can actually rewrite my D-bar operator eventually on this bit, and just get back into maps from the cylinder. So this again is going to be the information that's lost of a 0-1 form when you're close, when you're actually gluing. So that sits near the node. And then, right, what we do know is that essentially our D-bar operator, or our surface, or sorry, or section, you know, somehow wants to maybe, well, it's defined between these splicing cores in these two. But that really just comes from here, from the D-bar operator here. So this guy, we kind of, in order to define it between open sets here, we need to fill it. And that means, in this isomorphism, we need to decide what our operator on the sort of anti-glued data should be. And we'd like that to not really contribute information, so we'll just take an isomorphism here. That will usually be called nothing, F bar. So this guy here is, well, usually you just want to use it. That's sort of a general principle here. You know, whatever splicings you're trying, or whatever polyfold you're trying to set up, you know, anti-pre-gluing is probably going to give you your splicings, and then the filler is probably going to come from taking a linearized operator on the anti-gluing. So the linearized operator here is the linearized operator of D bar at my nodal point as a constant map, which in these coordinates on r times s1 I can write as ds plus j at the fixed nodal point dt. So that makes it a nodal operator, sorry, a constant operator, and it's explicit enough that we can ask ourselves whether it's an isomorphism. And it isn't, because there are constants in here that will get mapped to 0. Right? And that really means that I should have been a little bit more careful here. So there's some fiber product going on here also. No, actually there's, ooh boy, no, there's no fiber product going on. It's just because of that fiber product, there's something extra going on with these H3 maps on the cylinder, namely they're going to have to, you know, what is it? We're going to have to decay to 0, I think, at infinity. That is a lie, because I'm also allowed to move the nodes, so there's a little bit extra data in here, but you can still make a linearized operator. That's an isomorphism. So this is really sort of in quotation marks. That's the idea. So, given that description, one should now check that this is in fact a bundle and that this section here is in fact Fredholm. So do that first by realizing that this really is a very general kind of setup, and then go back into reviewing the definition of all these things. And so just for the underlying M-polyfold, right, we're taking a, well, you locally look at charts, right? They were given now by gluing parameters and this space, where is that? E. Right, this here is my E, right? And F is going to be the H2 spaces. So, right, so fiber-wise projection for every gluing parameter onto the kernel of the minus gluing, then that gives me the local homeomorphism to subsets of my ambient space, the polyfold. And I would now like to, describe the bundle over that in similar terms. And, oops. So that works very nicely. I should take the same ambient space, and then I have a fiber sitting here. And then in the base parameters, I should just take my retraction from down here. So the same projection that I had here also goes in here. And then I'm just adding a retraction on the fiber, which is going to give me the fibers over each base point. So in terms of anti and pre-gluing, this is then union over all gluing parameters, gluing parameter, kernel of the anti-gluing for the base, so for the maps, and then the kernel of the anti-gluing in the fiber, so for the 0-1 forms. So that's the idea. And, well, this really is, this is an M-polyfold chart for Y, but it's a special one because it comes really now just from a family of projections that's parameterized by the same gluing parameter as the one for the base space. And you can also sort of think that there's secretly a projection between the ambient scale Banach spaces. Well, there's different projections now, right? There's the non-trivial projections onto the kernel of the anti-gluings that give you the retractions and the splicings, and then there's sort of the bundle projections that just forget the value in the fiber. These are the simple projections here. And so my section is just defined between X and Y, which means since I only have homeomorphisms to these weird splicing cores, really a priori my section is just defined between these kind of strange subsets. It is of some kind of form, where, you know, it's only defined when, I guess, E prime is in this kernel of the minus gluing, which also is the image of the projection for gluing parameter A. We do already know what it means, though, for a map between splicing cores to be SC infinity, so we can ask for that. And we can also ask for the regularizing property, because we have, you know, regularity ideas in the fiber, and here we ask essentially for elliptic regularity. But we really can't even, in some meaningful way, talk about the linearization of this operator. So it's not defined on an open set. So that's why there's this idea of extending the map to a sort of filled section, and that should be defined for all E's, not just the ones in the splicing core. And that's what I'm going to call F bar. That's going to be the filler, or the filled section. Right, so this is the total section, that's the filled section. It kind of comes from deciding what you're going to do on the anti-gluing. So this choice here is the filler that fills the section. So that's our abstract, well, you know, abstract formulation of what I did, you know, in the Gromov-Witten and the Morse example. So now let's see whether maybe we'll sort of believe that these are Fredholm sections. So let's see. I need to say what a Fredholm section is, and that requires regularizing property, and it requires Fredholm filling, which we'll then need to look at more precisely. So, regularizing, again, just to spell that out, oops. You can talk about regularizing property, fortunately, in a trivialization. So, you know, with the way I wrote down my section here, right here, AE goes to F bar, or AE prime goes to, you know, F of AE prime, and maybe it should, well, this is essentially that's the D bar operator. So really, what is the right? So F here is sort of the composition of the pre-gluing in here, D bar operator down here, and then I'm putting a 0 in here and taking the pre-image. So that's my F in this situation, I guess. Well, F bar is the whole thing. F is the one when I have 0 in these components. Right, and that I would just like to say that if in the fiber I'm in regularity I, then my base point is already regularity I. And that makes a whole lot of sense now, because this here is D bar of something. Fi means it's H2 plus I, and this then is essentially a map, and EI means it's H3 plus I. So this is simply elliptic regularity. And then let's see what my claim is, that this gadget here is the Fredholm filling. Right, so that's the thing that at gluing parameter 0 is just a d bar in both components, and at non-zero gluing parameter it's the d bar on the pre-glued stuff and the linearized d bar on the anti-pre-glued stuff. You know, always taking this isomorphism back to get to the same space that this is in. So this here is on the sphere and the cylinder, and this is on two spheres, so I need to, you know, take that isomorphism back. So, what does it mean for that to be Fredholm filling? So, let's see. Well, right, so I somehow claimed last time that the retraction wasn't important in this case, but it actually somehow doesn't even make sense to talk about the rest of the condition without having a retraction. So this retraction is what? You're writing there's a retraction for the base of my polyfold, and I would like a big retraction for the total fiber space. This is the retraction for Y, to have the form little r in the base, and so little r in the base, that's just this guy, and then projections, linear projections on each fiber that are parameterized by the base. So each of the fiber spaces, these are linear spaces, are given by the image of a projection. Right? So linear projection pi. So right, so I've now have an ambient space on which my section is defined, and I would like to extend that my section to a map on an open set U. Right. So U here, right? Open set U. In our case, this is not, you know, corner structure here. This should just be, you know, some subset of C for the gluing parameters. And that we would like to be Fredholm in the sense that I define that just for nonlinear maps on open sets of scale Banach spaces. So. And then there's these three slightly confusing properties. Let me not repeat them, let me just say the first two. The relevance of the first two is that the filled section has the same zero set as a non-filled section. And the relevance of the third one is that the kernel and co-kernel of the filled section are identified with the kernel and co-kernel of the non-filled section, where it's not clear what I mean by this. So this, you know, what should it do, right? It should map from the tangent space to the splicing core that we did define, you know, as derivatives of paths to the fiber. But right, so this here, well, does lie in some subspace of this, and that is some subspace of F. But F isn't defined on an open subset here. So how do I get a map between those? Yeah, well, I could just take, I don't want to write this as, right, I'm going to just give you a formula for this. I could just take the derivative of my filled section, right, which is defined on an open set, and restrict it to that tangent space. Then that's going to map to F. and then I could just project to the right fiber. That's sort of a complete naive way of making something that should be the differential if it was defined on an open set. So what does this guy have to do, however, right? So there's this derivative of the filled section that I want here. This here now should have the same kernel and co-kernel as that one. And there it is useful to realize that there actually is a rather nice splitting. If I write this as a matrix, so I'm going to split the base into tangent space to the splicing and a complement, and I'm also going to split the fiber into the spliced fiber and a complement. And the cool thing is that there is one component that's definitely 0 in that matrix. That's between the complement of the base splicing and, is that right? Oh no, sorry, that's between, right, this comes from knowing that F bar maps the splicing to the fiber. So this is the part that maps from this tangent space to the splicing to the complement of the fiber. So there's nothing here. That's the good news. And then this guy here is what's in the first box here. And so now what we would like is whatever this here is to be an isomorphism, because then we can identify its kernel and co-kernel with that. And this here is in fact exactly this linearization that is asked to be an isomorphism. So it's the other diagonal term when I write the derivative of the filled section in this splitting. All right, so that's the meaning and the reasoning for why this is true was that, you know, we sort of made this part quite consciously by a linearized operator, you know, on something very simple like a cylinder that we knew was an isomorphism. So it's not only reasonable to use the linearized operator just so it looks nice analytically, it's also reasonable because that gives us exactly this isomorphism. So in particular now, right, I can ask for transversality. I could ask for this one to be onto, which is exactly the same thing as asking for the filled section to be transverse onto. And that's the definition of transversality. Right? So the game now is to write down somehow what regularization would sound like if everything were Banach manifolds, and just figure out the right meaning of Banach. So there should be a linearization, linearization that should be surjective, and lo and behold, that linearization is exactly this map where we took the filled section on the tangent tangents bundle to the splicing and then projected it into the right fiber. Right, it turns out that that actually is independent of the choice of the filler. So that's why it has this sort of other, just, you know, you could write the important parts that play in this linearization are really just the retraction composed with the original section. So that was the little dpf that I had on the previous slide in my condition 3 tells me that this means that in fact f bar is, well, transverse, which now is a map from an open set on Rk times to this fiber space. So that's now a transverse map locally, right? And then, well, I did boldly claim the implicit function theorem for scale calculus, right? So this is simply a nonlinear map between scale Banach spaces, and we know that it's transverse, so we just have to make sure that it actually is Fredholm. But that was Fredholm in the right way, and that's exactly, we defined SC Fredholm just so that the implicit function theorem holds. That was this retraction definition. So, right, so, well, what does the implicit function theorem now tell me? It tells me that the zero set, at least locally, is a smooth manifold. But then I have, the global theory that tells me that, the transition maps are scale smooth. And then I can, quote again the fact that in finite dimensions, scale smoothness is classical smoothness. So the transition maps on these local pieces of finite dimensional manifolds will actually restrict to just classically smooth transition maps. And so I get, a global smooth structure as classically finite dimensional manifold of my solution space. And, well, as usual, tangent space is the kernel of the linearized operator. So that is essentially the proof. So on some level, you do a lot of work, but in making sure that all the definitions make sense, because you make the definitions so that the theorems hold. So then the harder part is to make sense of the definitions. Well, and check the definitions eventually. So, and also the harder part is, not to know that a transverse section cuts out something nice and smooth, but to know that you actually have transverse sections. So the real beef of the regularization is this, I can find perturbations theorem. And if you start by just reading the blue underlined stuff here, then that looks exactly like the regularization theorem I've kept, stating. Well, except, there's this little bit of, so when I say proper Fredholm section, I mean zero set is compact. It's also part of the regularization theorem we always had, and so then we would like to, there should exist sections that are, so there should, perturbation sections so that the perturbed section is transverse, and then, by the previous theorem, that gives me a smooth compact. Well, it gives me a smooth manifold. I still need to worry about compact. And to get that compactness, there is an extra condition that involves a norm and a neighborhood and some, and then the neighborhood controls the support and the norm controls the size of the perturbation. But that all seems, to me, that seems very natural in some sense. Question is, what extra structure does one need so that norms by themselves can control Gromov compactness. And I'll mumble a little bit about that and sort of get through the invariance first, right? So there exist transverse perturbations, and then the question is, what if you have two different transverse perturbations? Well, there should be a cobordism between the solution sets, and as usual, that's going to come from a perturbation of the sort of parameterized problem. Right? So over x times an interval, there's going to be this sort of parameterized moduli space where I have a family of perturbations, nu twiddle of xt, so I guess nu twiddle of dot 0 should be nu 0, and when I put in a 1 I get nu 1. So it's just because of these extra conditions here, I also need to somehow say, well, these two sections will be controlled by some data, a norm, and a different neighborhood, and so this here, this nu twiddle, will also need to be controlled by some other norm n twiddle and u twiddle, right, which somehow interpolate between the ni and ui. And that's a little bit of a foreshadowing of the really disgusting uniqueness statements that we have in Kuronishi structures. Because we had to choose a whole lot of extra data before we made transverse perturbations there. And so then all the uniqueness statements, were dependent on this sort of hierarchy of extra data that we were using. And here, that's a little simpler amount of data. But, so, let's see. What does that data have to do with compactness? So, there's a bunch of extra words here. So, there's a word that says, I don't just want an M-polyfold bundle, I want a strong M-polyfold bundle. And right, let me say the simpler piece first. And we don't want it, before I always sort of talked about scale Banach spaces, but I always made sure that I'm actually making Hilbert spaces. And so, in this theorem, you actually do want Hilbert spaces simply for the reason that then in Hilbert spaces, we know that there are smooth cutoff functions. And that means in scale Hilbert spaces, there are scale smooth cutoff functions. Somehow the existence of smooth cutoff functions in Banach spaces is a classical problem. Hofer Wysotsky Zehnder didn't want to get into. So that's not so bad. And then, so this strongness has something to do with having an abstract notion of compact perturbations. Namely, there's a notion of not just scale smooth, but scale plus section, which is something like you should think in our setting, right? We had a first order operator. The scale plus section then should be a zeroth order operator. We expect to be a compact perturbation. And those, the size of these then gets, controlled with the norms to actually make sure that you're not put, the hard part here, right, is that this zero set being compact is a Gromov compactness statement. And you want to add something so that you're not losing Gromov compactness. So, yeah, that's where you really need to sort of go into the whole proof, I guess, of, well, you could go into the whole proof of Gromov compactness and try to make sure that's true. The nice thing is that in this abstract polyfold description, HWZ actually proved that in this abstract world there always are norms and neighborhoods that control compactness. So there's a lemma, or maybe another theorem. That says this data actually exists and is essentially unique up to things that are not so bad that you couldn't make cobordisms of it. So, right, so this description in terms of the scale Fredholm section is, you know, together with this notion of a strong bundle, gives you enough sort of abstract structure that you can, in an abstract sort of setting, prove that when you change your operator just a little bit, when you change your d-bar operator just a little bit, Gromov compactness stays true. And what you want to think of here is adding like a Hamiltonian perturbation term to your d-bar operator. We've all, well, some of us have seen proofs, but most people don't write up new proofs of Gromov compactness when you add a little bit of a perturbation of your d-bar operator. You know, you just add some lower order terms to things. You know, Taubes likes to add, you know, things to Seiberg-Witten equations that are lower order, and he doesn't. Well, he might go in and actually reprove things, but you know, most of us don't doubt him when we add some weird little thing that's geometrically relevant, but we sort of stare at it and say, well, it's lower order. It gets small when I rescale, so I don't see it in bubbles. I know exactly how it behaves when I break. This sort of belief that Gromov compactness still holds without me having to write it down actually becomes a theorem in this world, just because the thing is described as polyfold Fredholm section. So that really, to me, is one of the cool parts of this story. I now don't have to write something in my paper that says by the convex span of the ideas in 25 papers, well, maybe more in 5 papers, none of which write out all the details either. The following moduli space is compact again. So there is a little bit of, I put a bit more of an addendum to my slides where there's actually the definition of a strong bundle, and also then the stability theorem that says if I have a proper Fredholm section and add an SC plus section, it's still Fredholm. It's fairly uninstructive somehow to go through that. The main fact here in the strongness, so in our example, in the Gromov-Witten example, really because, so what is the fiber over a point U? Right, 0, 1 forms on U star Tm, where U, well, is usually in H3, it might be a little bit better. Right, so if it is in H3 plus K, the natural fiber over it, as defined by this whole splicing vibration, is actually the closure, right, in 1 degree less, H2 plus K, or 1 differentiability less. So let's say U isn't exactly smooth, right? Then U star Tm is actually not a smooth bundle. Right? It's only a bundle with transition maps that are about as good as U is differentiable. Okay. But U is H3 plus K, not just H2 plus K. So it does make sense to talk about the closure in terms of in the same differentiability as U does have it. Right? So this here, that's really, having this meaningful subset of that fiber is strongness. And this here then forms a sort of sub-bundle Y1 over X. And so where each of the fibers actually is compact in the fiber of Y. And so what happens is that our unperturbed section is a section here, and our SC plus sections will be sections here. That, in fact, is the rigorous meaning of being an SC plus section, being a scale smooth section into this bundle whose fibers have better regularity than this. So what we're thinking here is these are first order operators and these are zero order operators. That's the linear theory, right? And that the nice thing is that somehow goes across pre-gluing and anti-pre-gluing, and there's enough structure to preserve compactness with that. So I hope that convinces you that there's a good chance of this theorem being true. And what does that do now? Right? So you throw this Gromov-Witten moduli space at me, we make an M-polyfold description. We perturb it by something very, very abstract. But after the fact, you get a smooth manifold out. And one of the nice things is I never need to say that smooth manifold doesn't go through bubble trees or something. The bubble trees are just interior points of my polyfold. I don't care whether my zero set goes through them or not. I'm getting a smooth manifold out. I might care about that though. I might want to actually do something a little bit more specific here and somehow try to keep my solution set away from certain things, especially if I knew that unperturbed it didn't go through there. I'd like to preserve some geometric properties of my curves, like positivity of intersections in 4 dimensions. Knowing that they intersect certain hypersurfaces in nice ways. So that's where it makes sense to know a little bit about this proof. So eventually maybe there's going to be a whole list of things that you can do, or that extra properties that you can ask of these perturbations. But this is really the one proof that I think a user of polyfold theory has any business knowing, because that's where you can understand how to sort of refine your perturbation scheme. So, and the nice thing is that the proof is really actually sort of awfully short, because we're now in a setting where, right, if these were Banach manifolds at Fredholm sections, you would know how to prove this theorem. Well, maybe you've actually done this in finite dimensions. Right? And what would we do? We'd just write down a dense set of perturbations and then run a Sartre-Smale argument over a universal moduli space. So, abstractly here, I'm looking at pairs of solutions and perturbations. So, points in my polyfold and sections of Y. Well, I could just write Y1, let me say SC plus sections of my bundle. Right. So that, well, S plus mu of X should be 0. And then I have these extra conditions here. I'm asking mu to be supported in that fixed set. And I'm also asking nu, well, there's a norm here. Let me write that as sort of an infinity norm with respect to n. Well, I'm asking here, we're asking it to be less than 1, but I could also make it less than epsilon if I so wished. So I would use Sartre-Smale on this with respect to its projection to the SC plus sections. So the idea is to make that universal moduli space an honest-to-God Banach manifold, maybe a scale Banach manifold. Make sure that that projection is as differentiable as it needs to be in terms of index for the Sartre-Smale theorem. And then classical Sartre-Smale theorem tells me that the regular values are dense, and the regular value here is one for which this guy here is a transverse section. So that's the long and short of how that proof goes. The crucial part here is making this universal moduli space cut out transversely. So you need to look, at every, write this thing down, you need to look at every solution now, which is a pair of nu and x, and make sure that the linearized operator of this thing is surjective. And what you realize, if the linearized operator of S by itself is surjective, it totally doesn't matter what perturbation I add on it. This thing is going to be transverse. So that means I can actually force my perturbations to be supported only near where I actually have to fix transversality. So I could take a neighborhood not of the 0 set, but of those points in the 0 set where the linearized operator fails to be onto. So surjectivity is usually open, so not onto is probably a closed set, closed subset of compact set should be compact. So there's a compact set on which transversality does go wrong, but I'm going to need an open neighborhood of that in my ambient space. But I could keep that open neighborhood away from any other compact subset of my solution space. So in particular, if I have already a compact set of transverse solutions, my set of transverse solutions is probably not going to be compact, but so compact, I guess, subsets. So whatever large compact subset of it I choose, I could make the neighborhood not intersected, and so then these don't get touched by the perturbation. So this is really what Obamacare should be like, right? If you liked your solutions and they are transverse, you can keep them. And not only that, if you liked sort of your solutions, but they're not quite transverse, but they have nice properties, you can make sure that the solutions that are actually admissible in transverse look very much like your non-transverse solutions. So how do we do that? Right? Well, I can now shrink this neighborhood here essentially to, just that set where it's not onto. And I can also make this norm go, to 0. So I can find a sequence, certainly in which this norm goes to 0. And I didn't tell you what the norm is, but, and also with the support in open sets, which in the limit certainly lie within the 0 set, which shrink onto, a subset of the 0 set, I guess. And if I do that, then, all my solutions are going to lie within either the unperturbed solution set or this UI. Right? So they're all going to lie close to the unperturbed solution set. And that means every perturbed solution is actually very, very, very close to some unperturbed solution. This does not mean that near every unperturbed solution I actually have a perturbed solution. So you could have a whole big set of solutions, and after you perturb it, there's none. So this is inclusion in one direction. But if you know a property of the unperturbed ones, then you need to look into the polyfold topology and ask yourself whether this notion of nearness is enough to translate this geometric property to that, the geometric property of the nearby points. So, but it becomes not so much a question of what is the property of this perturbed d-bar operator. It's more a question of what's the topology in which these things are close to each other. And finally, right, when I said transverse here, I meant polyfold transverse. And so you're going to say, well, how do I ever know that things are polyfold transverse? And there is something that I've phrased as conjecture, but I realize that the part of this that is a conjecture is actually really not hard. So say you were in Gromov-Witten theory and you knew that all your holomorphic spheres by themselves are cut out transversely. Not necessarily the nodal spheres, because we don't really know what it means to be transverse there. But or say you're in Floer theory and you know that each Floer cylinder is cut out transversely. Then that really ought to imply that things are polyfold transverse. And this is something we can prove, I believe, pretty much. Because you can simply look at this crazy, filled operator here and try and look at its differential. So I have to vary the gluing parameter, I have to vary the two sections. So I'm going to say I'm only really worried about this statement at a glued at a nodal solution, so at a equal to 0. So I'm going to linearize this at little a equal to 0. And that means the linearization in the direction of the y's simply comes from the first line where little a is 0. And this is a completely understood operator. It's simply the pair of the linearized operators at the nodal curves. And then you get something extra. Yeah. Applied to the vector A from looking at, wow, what happens when A varies. Okay. But if these two gadgets here were onto, and they only act on y minus and y plus, I don't even need to know what this is. That's going to be onto by itself if I knew this. So I really don't care what happens with the gluing parameter. So this is not quite the proof. There is a hard part of it. So the reason I said remains to check, well, the reason I said should, is that there's something that remains to be checked, namely that this filler is actually Fredholm. And that then has something to do with linearizing this guy here at A not equal to 0, which is a little bit more of a bitch. And comparing this with the linearized operator at A equal to 0. So that's where you need to go through, the lemma that I gave you for, what actually is a nonlinear Fredholm operator. So there needs to be some uniform estimates. That relate the two. But let's see, what does that have to relate? So it needs to relate these two operators with the linearized operator at the pre-glued solution together with the linearized operator at the node. And so these relations here really are very much like the classical gluing estimates. One of the key things in the classical gluing is that you need to prove that this guy here has a right inverse and that some of its properties are uniform with respect to the gluing parameter A. And that's exactly the key part of the relationship between these polyfold fillers. So that's good news. We didn't just completely cheat away the hard work. Right? But the estimates that appear when you prove classical gluing now simply become part of the check that this is a Fredholm operator. And so then the actual proof of classical gluing just becomes part of the implicit function theorem for polyfold Fredholm sections. So we didn't cheat. Sweat is preserved, but it is distributed in completely different buckets now, so that when you then sort of try to change your operators a little bit, you can work in this language and hopefully more rigorously say that if I add a little bit to these operators, I'm not changing the estimates much, and that means I simply get scale Fredholm property again, and the whole theory sort of grabs you right there. So it's a language, and this was your crash course in that language.